Welcome to the May Smart Talks. I'm happy to introduce Aminreza from Dr. Hossein Rouhani's lab and Khilesh from Dr. Martin Ferguson Pell's lab, and they are going to talk about the wide world of wireless wearables, quantifying key metrics in athletic performance and spasticity diagnosis. And I will hand it over to whichever one of you would like to start.
Hi everyone, I'm going to start first. Let me share my screen. Okay. Do you see my screen?
Yep.
Hello everyone again. My name is Aminreza and I am a PhD student. Today, Khilesh and I are going to have a presentation on wireless sensors. And the topic, as you can see, is the wide world of wireless wearables, quantifying key metrics in athletic performance and spasticity diagnosis. I'm sorry. Today, I'm going to talk about in-field assessment of athletic performance using wearable sensors. Here in this presentation, I'm going to give you a big picture of a big part of my PhD studies, not all parts. First, I'm going to talk about wearable sensors and specifically inertial sensors. Then I'm going to provide you with a little introduction and a little background. And then I'm going to talk about my the technology expected outcome and deliverables of my study. Then I'm going to talk about technology development, and next, among lots of questions that can be answered and asked and answered in this area, I'm going to just answer two short questions, which is from two of the conference publications of ours. First question is a player joint angle interceptor repeatability in hockey, and the other question is about temporal event detection. Now let's talk about wearable sensors. What is a wearable sensor? Wearable technology, also known as wearables, according to Wikipedia, are smart electronic devices with microcontroller that are worn close to and or on the surface of the skin, where they detect, analyze, and transmit information, for example, body signals, and so on. Wearables has a variety of applications, as you can see in the pictures. They are applicable in like motion tracking, position estimation, heart rate monitoring, and so on and so forth. In this presentation, I'm gonna talk about inertial sensor. That's a kind of wearable sensor. Inertial sensor, or IMU, that is inertial measurement unit, is an electronic device that measures and reports body acceleration, angular rate, and sometimes the orientation of the body using a combination of accelerometer, gyroscope, and sometimes magnetometer. If magnetometer is included, in this case, it's called IMMU. Now let's talk about the field of my study, hockey. Ice hockey, as you know, requires high levels of aerobic and anaerobic fitness, well-coordinated body motion, and efficient functioning of the neuromuscular and cardiovascular system. Let's talk about hockey popularity. The International Ice Hockey Federation has 76 members. So it means at least in 76 countries, people play hockey. Particularly in Canada, 22% of households have a child playing ice hockey. So as a result, with the increasing popularity, improving in training and coaching strategies using advanced technologies like maybe inertial sensors or wearable sensors for objective performance assessment is necessary. To do this assessment, today we have different options. First of all is the motion capture system. The other option that we have is wearable sensors like GPS or even 3D accelerometer. Let's talk about advantages and disadvantages of all of these options. Traditional motion capture systems were used to do this assessment. It's stationary and uses camera and markers to find the trajectory to to find the kinematics of the player is precise and usually taken as gold standard. But it's just limited to capture, limited to a small part of the eyes, and it's not perfect for in-field assessment. So we can think of the wearable sensors. One of the most preferred technologies for in-field assessment has been GPS by now. If you want to find the position and velocity of the player, and if you it's a perfect choice, but it's perfect for outdoor activity. And if you want to find it, if you want to use it for indoor activity, the strength of signal is not good. And also, if you want to find joint angles and calculate them, it's not a perfect choice. The other option is 3D accelerometer. It's good for event detection, and you can develop some performance indices based on the accelerometer data. But if you want to find joint angle, or if you want to find spatial parameters, you need another sensor like gyroscope to fuse to this accelerometer. So as a result, inertial sensor, which is a combination of accelerometer and gyroscope, is a preferred choice in this case. IMU, or inertial sensor, has established clinical application, enabling us to assess 3D temporal spatial parameters, assess various aspects of gait like turning, anti-cycle variability, and it can assess, enabling us to assess 3D temporal spatial parameters, assess various aspects of gait, as I told you before, like turning, anti-cycle variability, and we can and we can obtain joint angles with high precision and accuracy. And we have this potential for in-field assessment of hockey performance, and we can use it for in this application. Our technology expected outcome is to obtain spatial temporal parameters and joint angles using IMU technology in training sessions. Also, this technology using IMU can help coaches to quantitatively monitor and characterize player performance in training sessions. And also, this technology can help us determine the distinctive kinematic parameters between the low and high caliber players. The deliverables of this study is to conduct in lab experiments that is done by now on synthetic eyes and then validate the technology accuracy to obtain spatial temporal parameters or temporal spatial parameters. And also, we can use this technology to validate technology accuracy to obtain joint angles. And using those kinematic parameters from like spatial temporal parameters and joint angles, we can develop some performance assessment algorithms, and then we can conduct analysis experiments to validate them. Finally, we can we can integrate this technology toward technology transfer. As I stated in the previous slide, the first step is to obtain and validate temporal and spatial parameters and player joint angles by the IMU technology in ice skating. To do this assessment, we built an in-lab ice rink using synthetic ice panels. As you can see here, this is the synthetic ice rink. And we provide all the required equipment and recruited 15 healthy participants to do skating for us. And also, we placed our wearable sensor, IM sensors on thigh, shank, and skate, and also pelvis of the player for all of them. Also, we placed reflective markers on the anatomical landmarks, and also we place pressure in sole into the skate of the player. These are our measurement systems. So we place 6 inertial magnetic measurement units, IMMU, on different segments of the participants, as I told you before. We use Xsense 3D motion tracking technology. Sampling frequency was 100 Hertz, and these sensors use MEMS technology to give us accelerometer, gyroscope, and magnetometer data. And you can see the full scale of these sensors in this table. For gold standard for temporal event detection, we use pedal pressure insole. The number of sensors in each insole is 99, and the sampling frequency is like inertial sensor 100 Hz. Also, for obtaining joint angle, the gold standard was a camera marker motion capture system. We have 10 infrared cameras in our lab, and the marker pressing protocol we use is Capozzo et al. 1995. The sampling frequency for our experiment was 100 Hz, like previous system, and the error of this experiment is less than 1 millimeter. So by using those experiments, we can answer different questions. But among lots of possible questions, I would like to answer just 2 of them. Actually, it's published in 2 conference papers. If you're talking about the performance of the player, the key assumption in kinematic performance assessment for ice hockey is the high intersubjectivity of the measured joint angles. But is it the case? It's not investigated by now, but by my understanding, it has not been investigated by now before this publication, and we investigated for 8 participants. Each participant has 5 trials in each session. This is the motion capture data, as you can see here. And you can see different joint angles of the participant during movement, during stride skating. And using CMC, or coefficient of multiple correlation, we investigated the intersubjectivity of joint angle measurement during stride skating and synthetic experiments. As you can see, all of these CMC are more than 0.6. It means that we can see good to high intersubjectivity in our experiment on synthetic ice for stride skating particularly. So as I told you before, we can see good to high intersubjectivity for our experiments. The next question, the next short question. Are the wireless inertial able to detect ice skating temporal events with high precision and accuracy? To do this assessment and to answer this question, we implemented 4 methods for highly cited method for gate analysis that they used IMU data for that, and we wanted to adopt and implement them to detect skate strikes and blades of during our experiments. So skate strikes is the time skate strikes the and hits the ice, and blades is the time that skate goes off the ice. We adopted and implemented a method from these 4 papers: Amini in 2002, Solari in 2004, Maria in 2010 and 2013. And these are the mean and ST of the error of this method compared to our gold standard. That here is the pedal pressure insole data. And the first table is for skate strike event detection, and the second table is for blades of event detection. Our observation confirmed that gate analysis methods are accurate in skating event detection application. We can find and they are able to detect skating events with 0.01 second error compared to the gold standard, and we can see higher accuracy and precision to obtain blades off in comparison with the skate strikes. And these are the 2 papers that I was talking about, and you can find it in the internet. These 2 questions for the first 2 phases of my study. The first two phases was validating the technology accuracy to obtain spatiotemporal parameters and to obtain joint angles. The progress rate for both of them are about 89%, but the papers but it's not finished and completed right now. But after the completion of the validation, we can use the spatiotemporal parameters and joint angles to develop performance assessment algorithms, and then we can conduct analysis experiments to validate them. And finally, we can do the integrate technology toward technology transfer, as I told before. As I stated earlier, wearable sensors have lots of applications. One of them is to diagnose muscle spasticity in the patients. Now, Khilesh is going to talk about it. Thank you.
Thank you, Aminreza. I'm going to share my screen now. Share and present. Okay, welcome to the wide world of wireless wearables part 2. I'm gonna say that only one time slowly because it is a tongue twister of my own choosing. Wireless wearables are really close to my heart because just about 2 years ago, I started wearing one to monitor my blood sugar, and it completely changed my life and 1,000-fold improve my ability to manage my diabetes. So there's such a huge scope in this niche of the industry. Wireless wearables really can help in many different applications. And I want to talk about one of those applications today, which is spasticity assessment. So I am a mechanical engineering alumnus from the University of Alberta. I'm working on Dan Gillespie's project right now in close conjunction with Dr. Martin Ferguson-Pell, who is doing hardware development. I'm doing software and algorithm development for Daniel's project to quantify key metrics in spasticity assessment. So what is spasticity? We're just going to go through the contents here really quickly. So I'm going to talk about what spasticity is, how it is currently diagnosed and treated, what the current challenges are surrounding that, and our hardware software bundled solution to those challenges, and where we are currently in the development of the project. So starting with what spasticity is. So the most common definition is a motor disorder characterized by a velocity-dependent increase in the tonic stretch reflexes or muscle tone with exaggerated tendon jerks resulting from the hyperexcitability of the stretch reflex. So just some quick stats for you here. 17 to 42.6% of stroke survivors 3 months past their stroke date suffered from spasticity. It's very common in patients of cerebral palsy and multiple sclerosis at a rate of 80%. And according to Johns Hopkins Medicine, it affects over 12 million people worldwide. So definitely a significant problem there. As for treatment, depending on if you're going for more of a global treatment or a local treatment, for global treatment, you have interventions such as intrathecal baclofen pumps, or oral medicine administration. For local spasticity, you have approaches such as Botox injections, which can be administered just depending on the case, whether it's more global or local. So how do we diagnose and assess this though? So in person, there are assessment challenges. So one that we are finding out increasingly due to the coronavirus pandemic is just the access problem. We know that, for example, in Alberta, a huge chunk of the population lives within the Calgary-Edmonton corridor, and as such, the specialists are also highly concentrated in these regions. So for people to get the care and the diagnosis that they need to travel quite far. And so the idea here is to enable more robust virtual assessment techniques as well. As for diagnosis, there are 2 scales that are currently used. One is called the modified Ashworth scale. In the definition, we saw that spasticity is velocity dependent. The Ashworth scale only takes into account the range of motion, but not velocity. The modified Tardot scale takes both range of motion and velocity into account. However, these are both mostly subjective, with the outcome of the scales um, being more or less at the clinician's discretion based on what they felt and their best judgment. So there's no gold standard clinical scale to identify just muscle tightness based on other physical factors versus actual neurological spasticity. And of course, the problems just get worse when you look at virtual assessment, which everybody has to do these days. The most common complaint is that the physicians, I don't know if it's the most common, but it's definitely very common. It's the physicians are just annoyed that they can't touch their patients, they can't be hands-on, and they can't diagnose that way. And there's also limited research as to virtual webcam-based methods. So initially, Daniel has held some focus groups just to see what some clinicians are saying, whether a hardware software bundle like this would be useful to them. So let's look at some of the data here. So 8 participants in the focus group. You can see the data is heavily weighted towards them not feeling very satisfied at all with what they're able to do. They're saying things that it feels like my hands have been cut off. Very unfortunate there. Technology is not equal in everybody's home. You know, somebody might be using a wobbly smartphone, and someone's caretaker may not know how to get the best lighting to, expose all the right angles to the clinician who's just trying really hard to do what they can with that webcam. So these are all problems here. So what if we can develop some hardware to obtain multiple sensor measurements to augment their ability to perform these assessments virtually? So we can send this device to rural clinics to minimize travel time, or directly to the patient's homes, so they can have the device and be walked through the process while the remote clinician helps them over the webcam. That's a possibility as well. Or if we just develop the device and just extend what the clinicians can do in person. So that's really the ethos of this project. Strong echoes of the telerehabilitation 2.0 just mindset here. We're really trying to extend what people can do, both in person and virtually, using better technology. So let's look at this figure over here. So you can see 2 sides on this figure, split down the middle. 2 cases are presented here. One where there is spasticity, and another where there's no spasticity, but there is an increased resistance through the range of motion of the patient performing the movement. So on the right side, you see that the patient is performing the movement. They go from a negative 30-degree joint angle to roughly a 20-degree joint angle, but they go up there smoothly. So it's a smooth movement. And on the force graph at the very bottom, you see that there is little to no resistance. And then at some point during the range of motion, they hit this resistance level, and then the force increases, right? And the EMG trace at the very top stays more or less flat. So like it goes up and down a little bit, but it's mostly a flat line that looks mainly like noise. However, when you look at the actual instance of spasticity, you can see that there's this beating activation of EMG throughout that joint motion. You can see that increase in the resistance on the force graph, very similar to the right-hand side case. But again, you can see these oscillations, and also the ankle angle here, you can see these oscillations. So this is something that the clinician would be able to feel and see, but previously they would have no paper record of this. And if there are biomarkers such as CLONAs that are available to use, we really ought to be able to record this and do some post-processing, and who knows, maybe other measures will be discovered as well. But really the key point here is to generate the technology so that we can record this information and enable better assessment of spasticity. So again, the question is, can we create a hardware-software solution that provides clinicians this capability to do it virtually and also enhance the objectivity of the in-person assessments as well? And I'd wager that we can. In fact, that is what we're doing right now. So I have two timelines here. One is the one on the top is the overarching timeline of the project as far as Daniel is concerned. So you can see here, study number 1, we did a virtual spasticity survey. We held a couple of focus groups, and we're squarely in this third phase now, which is device and application co-development. So zooming into this phase right now, this is where we are, and this is where I'm working. So we worked on the problem definition. We chose a platform to develop the software on. I've built the repository, and I have a minimum viable product now that can display the data in real time. So you can see the measures coming in from the device as the assessment is happening. And you can also save that for further post-processing in an Excel spreadsheet as well. So that brings us to essentially where I am right now as we speak. We have several measurement devices integrated within the device. So there's a force sensor that's online, that's working. We can get a force measure. There is an EMG sensor, which is also online working. We can get EMG measures, just gotta stick the electrodes on the muscle belly through the movement while it's being performed, and you can get that. But currently, we're not outputting the joint angle and joint angular velocity that the IMUs are present on the device to be able to do. So that's where we are at right now. So there's several ways to go about this, and we had to quickly shortlist a few and make a decision as to what way we would use going forward, as we're looking at a tight timeline here. So I'll discuss what our options were later on, and how we decided which the best one was to go forward with. But just so you guys can see, at the very top here, this is the receiver module. It plugs in via USB to the clinician's computer. It receives data from the bottom device here. The middle one is the transmitter board. The small piece here is one of the IMUs and the EMG sensor, and the other IMU and force sensor are also integrated in the middle piece here. So as you can see, it's wireless. It is independent and not physically coupled to the receiver at all. So the patient can, freely do their range of motion, wear it, and so on. So as I mentioned, we aim to get joint velocity, joint angle, and EMG and force, the last two of which we are already receiving in the software. So speaking of the software, this is what the software I've developed looks like so far. It has 4 windows corresponding to the 4 measures that are being received from the device. We have the EMG in millivolts, we have the force in newtons, the angle and the angular velocity. Currently I have placeholder values in here since the IMUs are working and we are getting values out of the IMUs, but they're currently not being synthesized into proper joint angles. So those of you who with a software background might be curious to know, we're using Windows Presentation Foundation, which is, you might know, just very convenient and a great option to develop Windows applications with. It's using the model view model architecture, which just really helps segregating the code in a logical way, maintaining the code because it's fully modular. If you need to change one part of the software, you have to do minimal work, and it doesn't create cascading effects through the rest of the software that you have to then go and change. It makes version management easier, and whoever is going to be developing this into the future will just have an easier time working with the repository. So that's why we made those decisions there. And on to what I was talking about with the 3 methods that we quickly shortlisted to obtain a joint angle measurement. Some are with current hardware and some are not with current hardware. So I'll just quickly try to go through each of these methods, what the positive and negatives are, and we'll do a quick decision matrix process at the end to find what the best one is and how we're proceeding. So the first one is a Quaternion based algorithm here. So just a very cursory introduction to the math. A lot of you might know already. A is just a placeholder for any element of the reals. That would be your real number. You add one term, a scalar multiplied by the imaginary number here, that gives you a complex number. And so a quaternion is really just a four-dimensional generalization of a complex number. So instead of just bi, you have a whole vector here, that which with each term is orthogonal to the rest. So the IMUs are capable of outputting the four elements of the quaternion. And if you have those outputs from both of them, in combination with the black box calibration algorithm they come with, you turn them on, they take note of their current position, and you take the outputted quaternions, you do a dot product, take the arc cosine, and that gives you the half angle. Theta is the half angle, so to get the full angle, you need to multiply that by 2. But that also means that if you have an error in the angle, you're also multiplying that error by 2. So it is slightly more error prone, especially when you consider that it makes the assumption that both IMUs are perfectly coplanar. So they cannot have a tilt with that XY plane respective to each other in their local coordinate systems. That's not very well tolerated by the algorithm. And in fact, even a little bit of tilt really exacerbates the error. So the advantages are that the math is really simple, relatively quick to implement, but you're quite error prone and you're making some limiting assumptions. So that's number one, quaternions. Number two is this method from Jakob et al., taken from a paper from 2013. They're a German group. They are using two IMUs, and the IMUs we're using have accelerometers, gyroscopes, and magnetometers all integrated into a fusion algorithm. And I think they use all three to come up with the orientation estimate. So the fact that you have a magnetometer here, it's well known that these can be affected by inhomogeneous indoor magnetic fields. So that's something to keep in mind. People have experienced volatility in their readings due to this. So back to the algorithm. So what's being done here is two calibration steps. First, you have the global joint coordinate system as defined by Groot and Sunday. So you have the x-axis of this red coordinate system being the rotation angle of the joint. Okay, and then you have local coordinate systems for the two IMUs. So the first thing is you take the gravitational vector, which is the output of both IMUs. You can get that output out of both IMUs, and you measure the misalignment of the G vector with the positive Z axis. And that shows you whether you're misaligned vertically with the overall coordinate system. And that misalignment is then accounted for using this RZ rotation matrix. The second step of calibration is an angle calibration. So the leg is lifted laterally at an angle a few times, and that allows you to assess whether the shank sensor frame is misaligned with the thigh sensor frame in the UW plane. So it's rotated about the Z axis so that the UW axes then match. And finally, your joint angle is computed as the intersection between the vertical components of the orientation of both IMUs. So right? Like this is a bit more of an involved processing thing compared to the quaternions, which was just one step of math. So on one hand, you have slight disadvantages like the process being slightly complicated. I mean, it's just math. It has a clean result in the end. But as for programming it, there's more snags that you could run into. And I've reached out to the team in Germany, the authors in Germany, for some support, just for some clarifications on some of these parameters. Although I have made strides in figuring out most of this myself, they haven't gotten back to me, and it's an old paper and they might not even get back to me. So that's always something to contend with here. Given enough time, we could crack this, I'm sure. It's just nice to have the support. So on the positive sides, we're not making very many limiting assumptions. Any misalignment in the axes is taken into account by these rotation matrices. So that's really good. A slight dearth in support is something you have to consider. and just high number of processing steps. So that's 2 of them so far, 1 more to go. This one is a potentiometer solution. Very easy, right? So a potentiometer is a voltage divider. You have a resistive track, and depending on the position of the rod, the dial, you have the contact sliding along the resistive track, and depending on where it is, that's how much your velocity, your voltage is scaled. And it is linear with angle. So all that you need to do is get the slope and intercept, slope intercept form of the equation very easy. The calibration only has to be done once, or maybe once every few months or something. And then the angle measure is very stable and reliable. And the process is also very well documented. And it's just very easy to build and code. It can be done in a couple of days, in fact. So how do we choose between one of these? Well, there's several criteria that we can look at. Some of them I've already mentioned, but let's go ahead and give them some weights and just in relation to their importance. So with processing steps, so I set this at a 3 out of 5 in weighting because it's relatively important. If there's a vast number of processing steps, especially involving matrices and matrix multiplication, and also in a programming language like C#, which isn't natively built to do these kinds of operations very efficiently, especially compared to something like MATLAB. The more steps you have, the more potential for setbacks. Not to say you can't eventually solve it, but it would just take longer. So that's a 3 out of 5 in terms of weight. Hardware availability, we either have everything we need to get all of these measures, or the parts that we require in addition are just cheap and common. So that's not a huge differentiating factor. That gets an importance of 1 out of 5. Accuracy is important. However, in several conversations with Daniel, it's clear that the relative dynamics of the data, like, for example, clonus, that oscillation in joint angle, the oscillation in EMG, those artifacts are those signatures are much more important than the actual precise joint angle itself. And all across the board, all of the methods I've presented quote a root mean square error of less than 10 degrees anyway. So it's not a huge differentiating factor again, but it's still kind of important. So weight 2 out of 5. Available support could mean several things, just depending on the project. So I told you I reached out to Jakob's team. They haven't gotten back to me, so that's one form of support. Other form of support could just be like a really well-written paper and something that's just really easy to follow. And you need support when you're working on projects. So that's just relatively important. I gave that a 3. So for assumptions, I mentioned some of the assumptions built into these algorithms. Like for the first one, there is that very limiting coplanar assumption. It can be a real big problem, for example, because the IMU right now is mounted right on top of the EMG sensor. But we know that with the EMG sensor, you need the freedom to be able to move this EMG sensor wherever, you get the best contact with the muscle belly. And with spasticity patients, we might have some physical abnormalities, which might lead to some unconventional EMG sensor placement. You really might need to place this EMG sensor anywhere to get a stable trace. And if you also have IMUs that need to be coplanar, but they're mounted with each other, that can be really difficult. So assumptions are relatively important, 3 out of 5. So can we build and test this in 4 to 6 weeks, which is kind of the time frame I'm looking at? Very important. We need to get the project done. And so that's supremely important. 5 out of 5 for importance. And then are we affected by magnetic fields? Because of the native magnetometer in some of these measures, it's important. So again, relatively important, 3 out of 5. So actually going ahead and crunching the numbers, don't worry, this is the last slide. I just want to go through and show you guys how everything scored with the set of criteria that we chose. So going through the Quaternion method now. As for processing steps, this is the leanest on processing steps. There's just one step, actually the potentiometer too, but it's just one step. So it scores very highly on that. Weighted out of 3, that gives it a score of 27.9 in that department. Hardware availability, we have the IMUs already, 10 out of 10. Accuracy, it has good accuracy. I forget the actual figure quoted, but I did use the actual figure in computing the decision matrix. So assuming I did that correctly, gets a score of 5 or 2.5, sorry. Available support, in the paper, they described it in one line, so that was a little bit challenging. I tried to code it. I'm currently getting a bug. I'm sure I can resolve it quickly, but the angle is coming out to pi every single time. So support, not the best, but it's also pretty simple and probably pretty easy to figure out why that's happening. So it scores an overall of 2. Assumptions, it has that one really brutal coplanar assumption, and I'm sure out there somewhere there is a quaternion method that mitigates some of these limiting assumptions, but with this one it's a problem, so it scores only a 1 there. Probably pretty easy to do in 4 to 6 weeks, so high points there. And is it affected by magnetic fields? Yes, it is, and I just went for a binary 0 to 10. High numbers are good here, so this one just got a binary 0. It could be affected by magnetic fields, and in fact, I saw somebody who was trying to do the same thing with their IMUs, and they were having issues that they surmised was probably magnetic fields. So I'm not sure how much of a problem it is, but as per the criteria, as defined, that gets a 0. So with the rotation matrix approach by Jakob et al., processing steps, lots of them, so it scores the lowest. Hardware availability, have everything already, 10 out of 10. Accuracy, they quoted good accuracy, but it's actually the lowest among all the methods presented here, which, might not be a huge deal in the grand scheme of things, provided, you get a lot of physical freedom, because the IMUs are not tethered to anything physically. So it's just an elegant physical setup overall. Available support too, they're not talking to me, I'm trying to talk to them. Assumptions, pretty high score on assumptions, because any misalignment in those angles are accounted for with the rotation matrices. Probably the hardest out of these to build and test in 4 to 6 weeks, which is a major concern, which is why it has low points there. And again, IMU's magnetic fields 0. So potentiometer plus stint solution, 1 processing step, well 2, but 1 you only have to do once, and then okay, 2 because you also have to compute a derivative once you get the joint angle. So high score there. Hardware availability, it's a potentiometer, they're cheap, they're just really easy to get. So high score there. Whoops. Yes, support, we don't really need support with something like this. It's just so easy to implement. You could figure it out with no instructions. It doesn't really make any bad assumptions. One is that you can't really put them anywhere. Like you could do an elbow joint angle estimation pretty well, because 1 stint would go on your forearm, 1 would go on your upper arm, and that's that. But what if you want to use a shoulder, for example? Where would one of those stints go? Would you tape it to the person's neck? I don't know. So slightly limiting assumptions, but mostly just forces coplanar movement because you're tethered to the stints. So medium score there. Build and test in 4 to 6 weeks, absolutely, really easy to do. And it's not affected by magnetic fields either, so high score there. So as you can see, the highest score out of this just very small short list of options. Again, there are many options out there. We just had to quickly come up with a few and make a decision and move on. So we chose a potentiometer for now. However, this will probably take the least amount of time to implement. So I'm hoping to be done this by next week. That should complete the wearable prototype. It should complete the software prototype as well, and really give Daniel what he needs to move on with the project. But with my remaining time, I can refocus on what are some algorithms we can use to leverage this really elegant IMU technology? What are some algorithms we can use for that? So I'll be going back to the drawing board, maybe trying to figure out if I can use first principles to get the outputs from that IMU to get a joint angle as well. And the repository is already set up with 2 GitHub branches for both. So everything's ready, and hopefully we can not only get a full minimum viable product out there, but also extend our rehab robotics lab's capability of doing some of this more sophisticated processing as well involving IMUs. So I hope you guys enjoyed this exposition into how we are using wireless wearables to empower clinicians to perform virtual spasticity assessments and enhance the objectivity of in-person spasticity assessments to hopefully change the paradigm of spasticity assessment going into the future. So thank you very much for your time, and have a great weekend, everybody.
All right, that was fantastic, guys. Thank you. So we will go to some questions. Anyone have any questions?
Yeah.
All right, go ahead, Michelle.
Yeah, my question for, sorry if I mispronounce your name, Aminreza?
Yes.
Yeah, so you're transmitting this information. What is your actual transmission method?
Uh,
I mean, it's wireless, but is it Bluetooth? Is it some other radio frequency stuff? What are you actually using?
yes, it's wireless, wireless sensors, and it uses Bluetooth to transmit information in
Okay.
field assessment. Yes.
So is it? I'm working on developing Bluetooth wireless, or I'm using Bluetooth wireless as well. But are you using the sort of regular Bluetooth or the Bluetooth low energy?
Actually, all of the system, all of the transmit and receive system is provided by the company. So actually, we do not do anything on that. But the only thing that we are cautious about is the distance that we can have between the transmitter, transmitter and receiver. So, and because of that, we limited our testing area on ice for our next phases. Yeah. And because of that, we limit our experiments for training sessions, not in matches.
Okay. And is it multiple transmitters or just a single unit that combines all of the sensor signals?
It's just one sensor and transmitter that's connected to the PC.
Okay, so it's all of your sensor signals are synchronized then.
Exactly.
Okay, very good. Yeah, so you probably are using the regular sort of standard Bluetooth, I think, because the data rates for low energy Bluetooth is really slow. So you can transmit at 100 hertz, but you're limited, and you often get dropouts. I worked with Khilesh on another EMG wireless sensor, and we were having problems with data rates. Still haven't solved those. And yeah, and Khilesh, the same question for you. Are you using the regular Bluetooth, or are you using low energy or something different?
Yeah, first of all, our I believe that it affects the result, but I'm saying that I'm doing offline
analysis.
Sorry.
Yeah,
Just offline analysis, not online. And because of that, we have all the signals in 100 hertz. Yeah, I know that if you are gonna do online experiments and online analysis, you need maybe you will not have, let's say, 100 hertz for all of your sensors.
Mhm.
I'm using 7 sensors, but now because I'm doing offline analysis, I have all of that.
Okay.
Did I answer your question?
Yeah.
Yeah.
Okay. Thanks.
I believe there's a question there for me as well.
Yeah.
Yes, we did work on that problematic Bluetooth low energy setup that we were having that issue with data rates with. It really caused that project to come to a standstill. So Martin actually since solved the problem by moving instead to the XB communication protocol. And to the best of my understanding, the XB communication protocol is just another protocol like Wi-Fi and Bluetooth. And it says here, Zigbee defines a network layer above the 802.15.4 layers to support advanced mesh routing capabilities. So it's just another communication algorithm. I'm just using their API, and it's no problem with data rate, anything like that. I'm just the receiver just receives it, the hexadecimal through the USB, puts it into the software, and yeah, no issues with frames dropping or anything like that.
Yeah. So your Zigbee signal is coming into a receiver that's plugged in through USB?
That's right. Yeah.
Okay, good. All right. Thanks very much.
Thank you, Michelle.
All right, any other questions from anyone? I have a really quick question for you, Aminreza. When you were talking about the hockey player analysis, what population is the target for that? Is this like for high performance athletes, for like the regular hockey players? Sort of what's the end goal with that?
It's one of our technology expected outcome that we can compare the techniques of the different players. So we can compare the techniques of the low and high caliber player using our technology, and we can find the distinctive parameters, the distinctive kinematic parameters that enabling us to let's say differentiate between the players. So
interesting.
yeah, so the target is both low and high caliber players.
Very interesting. All right, well, if we have no other questions, just so you guys are all aware, this is recorded and will be posted online on the Smart Network website. If you have anybody that was unable to attend, they can certainly catch up later. And with that, I guess everybody have a great afternoon and a great weekend.